Yeah, don't do that. Okay, do you guys all have class at 1:50? No. So I'll give you guys a choice. Do you want to start with like buffers and just softball one to warm up? Do you want to jump straight into titrations and then do KSP at the end, or do you want to start off with KSP since that's like the newest thing?
KSP.
Start with KSP? Okay. What is KSP?
Solubility.
Right, so what does that mean? In like non-chemistry terms, like something happens, right, when you're talking about KSP?
You want a solid that dissolves into its components.
Yeah, exactly. So basically, it's just like the equilibrium constant for stuff that's dissolving, right? Because dissolving is still a chemical reaction. Like you have some solid like sodium chloride, and then you dump it in water, it becomes sodium and chloride, and like there's physical stuff that's happening. So it's still kind of a reaction. So there is an equilibrium constant for that. So I wrote this one. Something. I know this isn't balanced, but there's the aqueous, so it's fine. What is the KSP for this? It's okay if you don't know, but
It's just the concentration of calcium 2 plus multiplied by the concentration of sulfate 2.
so you're saying it's is
And
it
it's
over?
over 1.
Yeah, it's over. Why is it over 1?
Because that's the activity of calcium, or the solid.
Yeah, and the activity of a pure solid is always going to be 1. So when you're doing KSP, if you have just a pure solid dissolving, whether it's calcium sulfate or sodium chloride or potassium, whatever, that's just going to be 1. So the only thing you're worrying about is the activity of the products. And one thing is that if your molar concentrations are low enough, then your molar concentrations can be substituted in for the activity. So in like physical chemistry terms, this is a little bit different, but in Chem 2 class full of not chemistry majors terms, this is fine. So you can just use the molar concentrations. So, I mean, that's like mostly what there is to KSP. Does anyone have any questions right off of that? Okay, then why don't we find like another problem? But I'm willing to bet that there's going to be like something on the exam that's like, what is KSP? And then you choose the answer. And then there's probably going to be something else that's like, write the equilibrium constant for this. Okay, who wants to do one of these? I'll talk you through it, but you guys will get way more out of it if you're the ones doing the problems. Somebody? Okay, yeah, thank you. Yeah, yeah, do that. Smartboard's fun.
Should I refill this?
So there's a little page button with the green plus. You can just press that and it brings, yeah, new page. Hi guys. So you have a reaction. We're gonna have calcium fluoride dissolving in water. So what's, yeah, you're close. What's the symbol for calcium? It's kind of like carbon, but it's the, yeah, Ca. And then the charge is 2 plus. So how many fluorines? Good.
What was it?
Water. We're dissolving this in water.
What was the?
Yeah, good. So the only thing I want you to add is all the states. So like solid, liquid, aqueous, whatever. Just 'cause that's important. Good. So what's the KSP for this? Yeah, good stuff. So why don't you put in calcium fluoride or water? How come you leave those out of the KSP? You're right. I just want to hear you say why. Yeah, and water's a solvent, so it's also correct. Yeah. It's also correct if you want to write this CaF2 solid going to Ca2 plus aqueous plus 2 fluoride aqueous. That's also correct. I mean, I know you're not saying it's like dissolving in water, but because of the fact you're saying these end up as aqueous, it's like they go what you're talking about. So thank you. That was good. So questions, comments, concerns on KSP? These are like giving points on these exams because for these, there's just one or two things you have to know. They're kind of like what you had before. So these are really good things to build up points for the harder problems, like the buffers and the titrations for like, you might miss something for sig figs or you run out of time or whatever. So these are definitely good things just to flashcard a couple times because you'll kick yourself if you miss that. Let's see another one. Okay. That's all I'm really going to do for KSP because you guys didn't talk about it too much. So between now and your exam, if you have questions about it, you can shoot me an email. But the buffers and the titrations and all that stuff is going to be a much bigger portion of your exam. And I feel like that's why you guys are here. So let's do some of those. So before I do this, what is a titration? Like, if you're in lab, what are you actually doing? Yeah.
It's usually with a strong base and a strong acid, and it's when you have the same amount of moles for each of the strong bases and the strong acid. Most of the
Yeah, so, yeah, pretty much. So you have like are you guys on lab? Did you do titrations at some point? So like, you have some amount of acid or whatever, the volume, the concentration, and then you're dripping base in, and then you have your indicator. So there's I don't know if you guys talked about this, there's two different things that happen. There's an endpoint and there's an equivalence point. What's the difference between those? Because that's kind of important for problems. Endpoint versus, yeah.
The endpoints where the color changes, the equivalence points where like the rules are equal to each other.
Yeah, which one comes first? Yeah, why does the equivalence point come first?
Because the indicator can indicators can be specific to it.
Yeah, that's it. But it's also like, so let's say I have 10 moles of acid and 10 moles of base. The indicator is going to change color because if we're titrating with a strong base, the base is going to react with the indicator after it reacts with the acid. Makes sense? Like all the base is going to react with all the acid, and then the base is going to react with an indicator, and that's when the color is going to change. So it's going to be a little bit more than the equivalence point, just because you can't get to the endpoint until you've reacted all the base. So when you guys are doing your titrations, you'll see like your numbers might be a little bit off because you're calculating the endpoint. Yeah? Okay, let's do a problem because you're all staring at me now. Who wants to do a strong acid, strong base titration problem? Because this one I'm definitely going to make you guys do. Somebody. Okay, thank you. Go for it. Page. Okay, so first things first, can you draw what this titration curve looks like? Strong acid, strong base.
Yeah.
It doesn't need to be perfect. Just like the general. Right, and where's the equivalence point? Good. And so that's the math, but like in real terms, what does that mean? Like,
pH is 7.
yeah, and then so you're dripping everything in and nothing really happens, then all of a sudden it changes really sharply and then it stops changing, right? So the solution we're working with here is 25 milliliters of 0.100 molar hydrochloric acid. And you're titrating that with 0.100 molar sodium hydroxide. And so did you guys talk about how there's like 4 different situations? There's initially, there's before the equivalence point, there's at, and then there's after. So what's the initial pH?
The initial pH of the H2O?
Mm-hmm. Well, yeah, of the solution. So we haven't added any sodium hydroxide yet.
Okay. So just take right, just take the minus log of the total.
Yeah, you just take minus log of the concentration of the acid. And because the acid dissociation is just 1 to 1 to 1 to 1, that's all it's going to be. Do you guys have your calculators? I didn't bring mine, so I don't know what that is off the top of my head. But yeah, good. One. Okay. So right away, pH equals 1. So now we're going to start adding stuff. We're going to add 24 milliliters of sodium hydroxide. So this is before the equivalence point. And then you can also, if you want more room, you can scroll up and down. And then when you get to the bottom, you can extend the page.
Okay.
So you don't have to just keep erasing if you don't want.
All right.
So after we add 24 milliliters, what's the pH? And just get us started. If you don't know what to do next, like we'll help you get through it.
Okay.
So you're calculating moles?
Yeah.
Okay. So that comes out to, this is actually a little bit easier. Have you guys talked about millimoles? This is easier if you do it in millimoles. And so the math is right. That comes out to 2.50 millimoles. This is easier to do in millimoles. Okay, and that's acid, right? Millimoles of acid. So now what do we do?
Basically same thing, but
2.4 millimoles. 2.40. And millimoles of what? Base, yeah. So we know how much acid we have, we know how much base we have, and are these are strong acids and strong bases, so they're going to totally dissociate, right?
yeah. So 2.5.
Yeah, so how do we do the pH from millimoles of H+.
We'd have to find the concentration. So 49 milliliters. And then
That comes out to 2.0 times 10 to the negative third molar. And what's that concentration of?
that's the concentration of H+.
Yeah. So if you get the concentration of H+, you can find the pH by
Taking the minus log.
yeah, taking the minus log. So that comes out to pH of 2.70. You're fine. It's broken. So now you're going to find, yeah, pH 2.7. So now the next part is actually at the equivalence point. So you have to do the math to show why it is, but do you guys know what the pH at the equivalence point is? 7, yeah, it's going to be 7, but you still have to do the work and show it. So, well, actually, I guess he probably won't make you. So if you know the pH is 7, you can just write pH is 7 because it's the equivalence point and it's a strong acid and a strong base. So now we're adding 26 milliliters. Well, so now we've added total 26 milliliters of sodium hydroxide. So find the pH.
Then it'd be. So we have 2.5, and then it'd be 2.6 millimoles.
Yeah, and that comes out to, what does that come out to? 2.0 times 10 to the negative third, again. So what's next?
You take the minus log of that, and then 14 minus that would be your pH.
Yeah, can you write just so everyone's like on
Yeah.
the same page? That is 2.70. So that's 11.30. I mean, I had different sig figs, but yeah, math is right. 11.3. I guess for you, it'd just be 11, right?
Or 2.7.
2.7, but for the 14, you don't have anything after the decimal.
Oh, yeah, no.
So it's probably just 11, right?
Yeah. Okay.
Is that right? I think so. Yeah. Good stuff. Thank you. Does that make sense to everybody? Any questions? Anything weird? It's okay. Yeah.
So for this one, you don't have to do a nice table because every reaction goes to completion.
Yeah, that's the fun thing about not using weak stuff. Everything's just assumed to go to completion, or like 99%. So we can't do a nice table because it's not going to go back at all. Once we do the reaction, it's just stuck. That's what it is. So we'd have to do another reaction to bring it back, but that's like a different type. That's called back titration. Are any of you guys chem majors? Nobody? Okay, well, if you take a CHE, okay, you can take a class called analytical chem, which is like this, but entirely different types of titrations. And so you'll do something called like back titration. So you can do it and you'll get like the amount of something, and you can titrate that again and then do a whole bunch of math. So for this class, you don't need to worry about that though. So it's pretty straightforward, the strong and weak stuff, but no questions? Everybody's good on that? You guys are all giving me 100% on the question. Okay, cool. Now we will do titration of weak. Okay. If somebody wants to do this one, you can. Otherwise, I'll give you a break and I'll do it. No? Okay. So for this one, we're doing 25 milliliters of 0.100 molar acetic acid. That's the abbreviation for acetic acid, but that's not like standard, so don't use that on your chin. But that's acetic acid. And then we're titrating that with 0.100 molar sodium hydroxide. So what's the titration curve going to look like? I guess you guys can't really show me, but it's going to look kind of something like that, right? Vaguely. So there's going to be this point here where pH equals pKa, and then we're going to have the equivalence point here. That look about right? Maybe? Some of you look like you have an issue with that. Is there an issue? Yeah.
For the last one, you know, you said pH equals pKa.
Mhm.
It didn't equal pKa at that point. Oh no, wait, we never used.
Yeah, so that was for strong acid and strong base. You don't have to worry about pKa at all, but because we have a weak acid here, that's going to come into play a little bit. But we'll do the math, and you'll see how that works out. So the first thing is just the initial pH, right? So pH is going to be the log of concentration, but because we have a weak acid, we have to do an ice table. So CH3, COOH plus H2O is going to go to CH3, COO minus, and just H3O plus. Right, so we're starting off with 0.100 molar. We're not going to have any of that. And then we're going to lose how much? Initial change, equilibrium. How much are we going to lose? X. We're going to lose X. So this is going to be 0.100 minus X. Here we're going to have 0, and then we're going to gain X. And then that's just going to be X. And then 0, and we're going to gain X. And that's going to be X. So we have Ka is equal to X squared over 0.100 minus X. I'm going to make the assumption that 0.100 minus X is approximately equal to 0.100. So this is just going to become X squared over 0.100. We solve for all this stuff, and we get X equals concentration of H3O plus, which is going to come out to I did it on my calculator, so I just didn't write it down, but pH is going to be the negative log of that, and you get 2.89. So if you guys are doing this in your notes, that's how you do it. I didn't write down the concentration. But
Plus K.
the K, I think it's 1.8 something. I don't know. I know that memorized. I did it all on my calculator, but they will give you the Ka on the exam. Yeah.
In general, when do you know that your initial H3O is 0 compared to when it's not 0?
So typically when you're talking about initial, it's pretty much always 0. It's just like, this is like after 1 nanosecond, like nothing's happened. This reaction hasn't actually gone yet, so it's going to be 0 and 0. And so that's how we know that the change is going to be minus X. Because if there already was something initial, we couldn't say the change was minus X. That'd be like minus X, then there'd be a Y variable, and it'd be all J and E. So when we're talking about initial, we're saying like the literal second these come together. Make sense? So that's initially. Now we're going to add. Now we're going to add 10 milliliters of this 0.100 molar sodium hydroxide. So we kind of did this before when he was doing his problem. How do we want to start this off?
Multiply it together.
Multiply what together?
10 milliliters, 0.100 molarity, you get millimoles.
Right, so calculate millimoles of acid and base. Is that what you're saying? Okay. So 0.100 molars times 0.1, actually, just do times 10 milliliters is going to come out to 1.00 millimoles of hydroxide. And then before we had 25 milliliters of 0.1 millimole per milliliter, which is going to be 2.50 millimoles of acetic acid. Makes sense so far? Good on basic algebra like that. The thing is, for this one, we can't just subtract because now we have actually, no, we can't. This is a strong base. Never mind. We can't just subtract this. But I'm still going to make a table. So we have our acetic acid. We have our hydroxide. And that's going to go to acetate and water. So initially, we have 2.50 millimoles. We have 0, we have 0, and we don't care about water. So then we're going to add 1.00 millimoles of this. So then the change can be -1 millimole, -1.00 millimole, and plus 1.00 millimole. Everybody's good on that? We add in 1 millimole, so we're going to lose a millimole of acid. We're going to lose a millimole of the base once we add it, because it's all going to react. Then we're going to gain a millimole of acetate. Good to go, because it's a strong base. Okay. So then after, we're going to have 1.50 millimoles of this guy, 0 of this, and 1.00 millimoles of the acetate. So the concentration of the acetate is going to be 1.50 millimoles over, let's see, our total concentration is 35 milliliters, which comes out to 0.0429 molar. And our concentration of, well, this is the acetate technically. Our concentration of acetate is going to come out to 1 millimole for 35 milliliters, which is 0.0286 molar. Good so far? Yeah.
Yeah. So if you have a strong base and a weak acid, you can subtract the amount of strong base that you have from the weak acid. It doesn't matter that it's a weak acid.
It doesn't, because it's a strong base. There's actually a thing in the book. It's like bolded. I should have written it down, but I'm going to read it to you guys because they say it a lot better than I can. Okay, for equal volumes of acid solutions of the same molarity, the volume of base required to titrate to the equivalence point is independent of the strength of the acid. So if you're using a strong base, it doesn't matter what type of acid you have, whether it's a weak acid or a strong acid, the volume of base you need doesn't depend on that at all. So as long as one thing is strong, then it doesn't matter what the other thing is. Good to go? Okay. So now that we have these guys, we can use our favorite equation, which is the Henderson-Hasselbalch equation. So what is that? Somebody off the top of your head?
PK plus the log of the concentration minus J.
Yeah, good. So how do you find pKa? How do you find the P of anything? Yeah, the professor I had for one of his classes did something really goofy, but it's how I always remember. You take the negative log of dog, you get P dog. I don't know why, but that's how I always remember that, so maybe that works for you. So yeah, the Ka and all that stuff will be given to you, but for acetic acid, it's 4.74 plus log of 0.0286 over 0.0429. And this comes out to 4.74, which equals the pKa, right? So somebody was asking about this earlier. So that's what we just found. So it's before the equivalence point. There's a point where the pH is going to be equal to the pKa because, well, you saw why we just did the math. But that is the point we're talking about. So the next part is going to be at the equivalence point. So we're going to add, oh, sorry, no, it's going to be after. So, oh yeah, I should put the point that we just found is the half equivalence point. The half equivalence point is from the pH equals to pKa. So now we're going to do, we're not going to do at the equivalence, but we're going to skip it and go to No, we'll do it. We'll do 25 milliliters of sodium hydroxide. And so this is the equivalent. So, oh, okay, so actually you guys tell me. How do you find KW?
K times KB.
Equals K times KB. So if we want, oh my god. If we want KB, how do we find that?
Divide KW divided by KB.
That's KB. Sorry, what did you say?
KW divided by KB.
KW divided by K. So KB equals KA over KW over KA, sorry. KW over KA, which for us is going, they'll give you all the stuff on the exam, but for us, that's going to come out to 5.6 times 10 to the negative 10. And so the actual equation that the chemical equation that we're looking at here is HA plus OH minus is going to go to H2O plus A minus, where A minus is acetate and HA is acetic acid, right? So KB is going to be equal to the concentration of acetic acid over the concentration of so let me make sure I'm doing this right. Yeah, for the KB, it'll be this, CH3COO minus for KB. And so we get x squared over 0.0500. So we calculate x, which is concentration of OH minus, which comes out to 5.3 times 10 to the negative 6. So pH is equal to 14 minus the log of 5.3 times 10 to the negative 6, which comes out to 8.72. That's the pH here. Good stuff? Okay.
I have a question.
Yeah.
Why is it x squared AB? Like, is there another, like on top, than like for KB?
Why is it x squared?
Yeah.
So this is what actually is happening, but we're writing the KB, which will be this equation. So here we'll have x squared. I mean, I wrote it here because this is the way it's happening, but since we're solving for KB, it'll be this way. So we'll have x and x.
Oh.
Make sense?
Yeah.
Yeah. Does everybody get why we did that? That's a good question. Yeah.
So x squared over 0.0.
50,
Yeah.
sorry.
So like is that like that equation is in equilibrium and we're assuming it's going in this direction?
Yeah, sorry about that. We're writing, yeah, I shouldn't have written it this way, but we're writing it for the base reaction. So where this is the, I know what I'm trying to say. I'm just trying to say one grain. Give me a second.
Like Dr. Zion, he switched it up so it's like the conjugate base reaction. It involves with
Yes.
H2O.
Yeah, that's what I'm doing. I'm drawing a blank on how to explain it.
Would
So-
it be like CH3COO minus plus H2O, there's OH minus and CH3COO?
That's the one.
Yeah.
So I don't know why I'm blanking so hard, but later I'll write it down. I'll send it to you guys or something. But that's a ring there, 8.72. So the final like situation we're gonna do is after the equivalence point. So now we have 26 milliliters of sodium hydroxide. So I feel like you guys are getting tired of hearing me talk. Does somebody want to finish up the last part? I can do it if you want, but
I'll try it.
I know when I go to SI sessions, if I'm just like sitting there like it's a lecture, I completely zone out. So I can't blame you guys.
So it's 26 milliliters of
Sodium hydroxide, and remember the concentration is 0.1 molar, or 0.100. It's okay if it's not like perfect. The smart board's always a little finicky, so as long as we can kind of read what you're writing, that's fine.
so like that. And then
Yeah.
it was, what was the molarity?
0.100.
And then do you want me to do the table? Because I like doing the table.
If you want to, I mean, as long as we get the right answer, I don't really care how you do it.
You've got,
It's not super important, but can I give you guys a mini organic chemistry lecture? Because we're talking about acetate, and actually, I'm the SI, so I'm just going to do it. Acetic acid is this guy, right? So we have CH3COOH. So what that means is that we have a carbon here, we have a carbon here, we have an oxygen here, we have an OH here, and we have 3 hydrogens here, right? So this is what acetic acid looks like. And you guys have a couple different ways of writing it. You can do ACCOOH. You can just write acetic acid. You can write CH3COOH. And I know it's annoying to do it, but you don't want to lose like half a point or something because like you forgot an H or a C or something.
I tried.
There we go. So just be super careful when you guys are writing the formulas and everything.
This is a strong base with a weak acid, right?
Mm-hmm.
So I'd have to switch the formula, right?
What do you mean?
Like, I would have to change it around because you can't have a negative concentration because you would subtract.
That's the first one though, like switch it when you're figuring out, when you're after this, because you have to first figure out how many moles of which either is the limiting reactant or
Well,
what's not limiting reactant left.
Then you would do, like, you would subtract this.
When you subtract the 2.5, because
Yeah.
if you subtract by 2.5 minus 2.6,
Yeah.
it's negative.
So
Yeah.
it's not like what you're adding, it's what the limiting reactant
Okay.
Yeah, that's right, and that's a good point. But yeah, they're right. So if you have, I mean, do we all remember what limiting reactants is? It's okay if you don't, but one thing's going to run out first, and so that determines how much you can make. So if we have 2.6 milliliters of, or millimoles of the strong base and 2.5 millimoles of the acid, it's 1-to-1. So the 2.5 is going to run out first. So that's the change. So she's doing it right now. That's good. Yeah, it's so weird when like you write like a straight line, it's just like wah wah.
Why do we use this for? Why can't we use a normal like?
Because then a lot of SIs like type up their stuff before they come. Sorry guys. But if they want to do that, or like some people will like open up the book and work through problems on this, and it's easier to do it that way.
Well, people are stupid. So then it would be 51.
Yeah, which comes out to, I actually don't know. I don't like calculator because I did it a different way.
0.00196.
It's, what is it?
0.00196.
0.00196.
Yeah.
Oh,
Oh yeah, one more zero. So 0.00. So the one's the thousandth. Good.
Better.
Yeah, good.
Anyone want to help me out here?
0.0490.
0.0.
490.
490.
Okay. And so that you got your concentration.
Somebody take the negative log of that.
Anyone want to help me out with the number?
Negative log 0.019. 2.71. So how do you find pH?
And then you have 14, 0, equals to pH plus pH. That's much better. You have
So why are we doing ice table afterwards? Because
You don't have to do an ice table, but I always do an ice table because it's like more visual for me. You don't have to.
would it still be have to be the same thing?
Yeah, because we're just doing addition, subtraction, so it'll come out to be the same thing. All right, so the whole point, yeah, that's right, really good job. Awesome. The whole point of doing like the ice table for these is just so that you can see what's happening, like you can see what you're adding, and I'm a big fan of writing down literally every single thing you do on the test because you can eke out as much like partial credit as you can. So when in doubt, do the ice table because like doing it in your head or just doing the calculations, like it's great if you can, and eventually you should be at that point, but on a test, it's really easy to make little mistakes like 7 plus 7 is 77. But if you do stuff like this, it'll just help you make sure that doesn't happen. So that's the super long answer. But how's this look to everybody? Any questions? Yeah, you first.
So like after you have the OH minus concentration.
Wait. Before you leave, can you sign in for me, please? Thank you.
So like after you had the OH minus concentration,
Uh-huh.
then like before it wasn't like I remember back then I did like an ice table after.
Yeah, that's what I was saying.
So he did an ice table. Was it the same situation? Or
I'm not sure.
Yeah, I'm looking at my notes and we did an ice table.
can I see somebody's notes?
Is there any RGB access to this?
So
You did one with KB using KB.
Yeah, that was correct. Because I think that one was just excess conjugate. I don't think there was any excess strong base.
For this,
Well, this one we have excess strong base.
and we have conjugate. as well.
We also have
Yeah,
IB
I know.
involvement.
yeah, let's keep going. So this problem is HF and sodium hydroxide.
Yeah.
Your notes are so neat. I've never taken notes in my entire life.
Thank you.
Mine are like 80% changers.
So that reminds
So plus the.
No, I just haven't felt even more.
No, because if you look at all we have is excess.
So you can
No excess. That's why you get we have excess. With this, you have to do excess.
To be totally honest, I don't know why you would do that. I think it does have to do with something in excess, so why don't you, if you want, send me the problem, and I'll stare at it for a little while, and I'll send you an answer. But off the top of my head right now, I don't know why you would do that, but I have a feeling the answer would come out to be the same thing. I don't know.
shouldn't it be a higher? Shouldn't it be a higher pH because they have excess NaOH?
You have conjugate base as well.
Yeah.
You do have excess base, but that's a really high pH. I don't think it would be higher than that.
Is it just because it's a high pH that it just like doesn't matter?
I think it's also because you would have the conjugate base, but the conjugate base would also be pushed out a little bit because Le Chalier's principle, right?
Yeah.
You have a whole bunch of base in a basic environment, so I think some of it would get pushed out. Maybe that's what you guys were calculating. I don't know. But I think some of it would go back as Le Chalier's principle. Oh, send me that problem and I'll think about it and I'll send out like a mass email as to why that is.
This problem?
Yeah, can you do that?
I think it's the excess strong base, because I don't remember having that excess strong base in class.
Maybe.
Because he didn't do any like problem where there was more base. He just did the equivalence point.
Mhm. I don't know. Yeah, send me that and I'll think about it. But
There's a problem with that that's happening though, where there's more than the equivalence point.
can you screenshot that for me and I'll do that one and I'll tell you guys how to do it tonight. Okay. We still have time too. It's okay if you guys have to go, but there's time for more questions and things. And if you guys are leaving now, please sign in for me. And you can email me over the next couple days if you need anything. Looks like you guys are done. What are you so confused about?
The part we just did. Yeah, like the, so why we did it.
Why you guys did the extra ice table?
Yeah.
Oh, it's not an ice table. It's just like subtracting.
Well, yeah,
Alright,
there's that.
good
one,
luck.
but then
Don't forget to
after
sign
that,
in. You can
I
email
just-
me.
Do you sign
Oh,
it? Yeah, do you sign it?
It's floating around, honestly. Somebody has to sign in sheet. Yeah.
Thank you.
Yep, email me if you need something. Good luck. Still have time, so you guys don't have to give. Can you come up here? I can't hear you. I'm sorry.
Yeah, I have a question, but I think it might have been already explained.
That's okay.
So, but there's still some confusion about it. So after we find the stoichiometry, we use the ice table, right? Well, you can use the ice table, or you can use the hash.
Well, like which like situations?
The ones that we just.
Which part of the situation?
So
It
for
depends.
not initial, like whenever we're adding, it's say we test, we're adding strong base,
Mhm.
we need to find the stoichiometry and then find the equilibrium, right? So for the equilibrium, we can use usually ice like chart, right?
Right.
We can also use the Hasselberg and Hasselhoff's equation.
Henderson Hasselbeck, but that's
Yeah,
yeah.
sorry.
Everyone calls it something different. It's Hasselberg, it's Hasselhoff, but yeah.
So,
I think that's right, but I want to avoid any like broad sweeping generalizations, just because A, I'm not totally sure, and B, you might come across a problem with like a slightly different thing. And if you have a generalization in your head, then you might necessarily design problems to do that. So I would partially yes, but try to look at the chemistry of what's happening and see if it makes sense, you know?
Like, I think like the thing that like they were talking about is like we did like a table like that, like just like that, but it was like to find the stoichiometry, and then once you found that, then you did your ice table.
Mhm.
So like,
I was asking more of, I guess, what's the relationship between the equation and the ice table?
The ice table is like the visual representation of of the equation, I guess. The Henderson-Hasselbeck equation is just showing like you got your pH, and then based on the changing concentrations of AJ and A minus, what's the pH going to be? The ice table is just like visually like going through every little piece of it. So yeah, you could probably use the Henderson-Hasselbeck equation, but
And those, so, and I might be confusing different parts of the chapter too, but for the concentrations that go into this equation, so you have your base on top and your acid on the bottom.
right, yeah.
And so this base is the one that's left over, the one that's used, or the one that's initial, the concentration. And on the bottom, the acids, you know, you mentioned like sometimes it's the one that's used, or,
I think it's the one that's going to be floating around in the solution at the time, because the one that's used up, if
okay,
you plug that in, that's not technically in solution, and if it's used up, that means it's becoming acid. So you're kind of like doubling the amount of acid you're gonna use, you know what I mean?
Yeah.
Because like saying base that's used up in acid form is like the same, two sides of the same coin. So if you're adding both those together, you're actually just gonna be increasing the pH, you know?
Yeah.
So, I know that doesn't really answer your question, but try to just look at the problem and go through the chemistry and like think about the pH and see what's actually happening. And if it's not making sense to you what's going on, then do the ice table, you know, go through every step and you can prove it yourself. And if you can't, good luck, I'm gonna need it. So the ice table is an easier way to make sure you're checking all the boxes, you know?
Okay.
Because you can see it happening, and you have to tell yourself, like, there's no base form here, so I can't plug that in, you know what I mean? The Henderson House back way is a good way to do it, but use an ice table, like,
It's more sure you know which concentrations are going where at what time, instead of memorizing necessarily what goes in.
it's like writing down all the units, going through all the steps, doing everything, and just plugging it into your calculator, like 9 steps straight, you know?
But we didn't end up doing an ice table for the last one because we had excess OH. Would it be possible to do an ice table for that one just to kind of see how it plays out the excess?
I think it depends on what you mean with the ice table, because if you're looking for something with equilibrium,
Yeah.
if you have a strong acid or a strong base with anything, there won't be
The
equilibrium.
It'll
So
just be
it's not really an ice table, it's more like an ice concentration after table, you know what I mean? Like, you see how we did it here, we had like 2 different things on the side, like, yeah, you can start, you can add, you can change, and you have what's going on
Yeah.
afterwards. So that's just like an easier way to lay out all your work.
So in any case that you have, say, weak acid strong base, weak base strong acid, if your strong acid or your strong base goes above the equivalence point, then we are left in this situation where you could just take the direct concentration that's left over and convert it into pH or POH.
Yeah, because at that point you won't have, you know, if you have excess strong base, you won't have any acid. So-
Polyprotic
Okay, well, polyprotic is a little bit different, because with polyprotic, you're assuming that, so do you guys know what polyprotic acids are?
Yeah.
Acids with, okay, so a polyprotic acid, you gotta stop me. I will go off on tangents. Yeah. So that's something like phosphoric acid. Polyprotic, many protons, H plus is just a proton, right? So polyprotic means that you have multiple protons to be donated. This is really different, and it's partially different because you're assuming that the first ionization, like the first H3O plus going to H plus and H2PO4 minus, that first step, we're assuming, is the largest change in pH. Like, that's where most of the acid's being donated. But at the end, you still have an acid. Things can still happen. So it is different. I have one of those in my notes. So if you guys want, I can like photocopy that and send that out to you guys if you want. I can do that. We won't be able to finish it now, but if you guys want to see it, yeah, I could do that. And I can like find videos on those and send them with you guys too.
Yeah. Yeah.
How do you guys feel about this exam, actually? Okay, thanks everybody who's listening. Email me if you need anything. I send you like 2 emails a week, so you have it.